In the first lab, we discuss how ordinary objects can become charged. When you pull apart, as we do in this lab, rub or touch objects in your daily life, they can accumulate charge. In this lab, our job is to determine just how much charge these interactions create. We will be exploring charge on everyday objects to determine how much excess charge is on a piece of tape when they are pulled apart. To do this, we need to know some fundamental physics principles, such as Newton's first law that states an object at rest will stay at rest unless acted on by an outside force, and using conservation of charge principle that states that a charge cannot be created or destroyed. Finally, we will calculate the charge. We know that our answer should be between the charge of one electron, since we know more than one electron is removed, and less than the charge of if all the electrons were removed from the tape, because this would destroy the tape. Some other fundamental things we need to know for this lab is that the charge is generated by elementary particles such as electrons and protons, and that these form electric and magnetic fields. We also need to know that these fields radiate from the source charge in all directions. And finally, in electric forces, like charges repel each other and opposite charges attract each other. We need to start by determining some basics about the charge of the tape. To make a charged tape, a piece of tape was placed on the table. Another tape, a U-tape, was then ripped from the bottom tape. This piece of tape was then attracted to a neutral object such as your hand. When we did this with two pieces of tape and found that the pieces repelled each other, then we brought them close together, telling us that the pieces of tape had the same sign. To determine if the tape was negative or positively charged, we used the pen. When you rub a plastic pen in your hair, it becomes negatively charged. The tape is attracted to this, meaning it has a positive charge. For this experiment, we used our two charged pieces of tape. One of the pieces of tape was placed on the top of the two plastic bottles. The other piece of tape was held under the tape, suspended between the two bottles. Because the tapes had the same charge, the tape on top appeared to float because the electric field from the bottom tape. Now we need to talk about the forces on the tape. For this experiment, we are only looking at the forces in the y direction. These forces are gravity and the force of the electric field as shown in the free body diagram. Since the tape is not moving per Newton's first law, we know that the net field force must be zero, and therefore the forces must have the same magnitude in opposite directions. We must first determine the important measurements before we can do our calculations. First, the length of the tape is 0.18 meters. Using conversions, we were able to find that the mass of the tape was 0.0018 kilograms, which is useful for the calculation of the force of gravity. And experimentally found that the tape was floating when the tapes were 0.02 meters apart. These measurements can be used in our formulas for the force of gravity and the force of the electric field to calculate the charge of our tape. For this problem in the electric force formula, we can use Q squared because we know that the tapes have the same charge. So because we know the object is at rest, we know the forces are equal and can set our formulas from the last slide for the force of gravity and the force of electricity to zero and isolate for Q. When we do this by hand, we get 8.85 times 10 to the negative 9 coulombs. Next, I set up a code that allows us to display the forces look like on a piece of tape. In lines 3 through 6, I specified some constants that are needed for calculations. In lines 10 through 11, I created pieces of tape, treating them like point charges. Lines 16 and 17 calculated the force of gravity and created an arrow to display it. In lines 19 through 21, I isolated Q and calculated E force with the Q found in the program. It starts by finding R, the magnitude of R, and R hat. This uses the algebra from the previous slide to find Q. In lines 24, we have our formula for the electric force. And finally, in lines 25 and 26, I generated the arrow to represent the E force and the R vector. In lines 31, I input the position of my piece of tape and run the code. This is the output of my code. The red ball is the floating tape and the blue ball is the tape creating the electric field. The charge on the tape as found in the program is the same as my charge calculated by hand. Next, based on the Q, we calculated the number of electrons that were transferred from one tape to the other electrons, then found the total number of atoms on the surface of the piece of tape. We then can use both of these numbers to find what percentage of atoms had electrons stripped, getting a result in our expected range. Finally, we need to go over our assumptions and our sources of error. Our assumptions include ignoring a resistance on the top tape, treating the long tape as a point charge to simplify calculations, and assuming the tapes have the same charge. There are three major sources of error in this experiment. The biggest source of error is touching of the tape, which occurs when setting up the experiment. When you touch the tape, the ions cover your skin by travel onto the tape, canceling some of the charge and making the tape more neutral. This leads to loss of charge in the tape, making our results somewhat skewed. The other two are inexact measurements of when measuring how close the tapes must be for interaction and inexact alignment of U-tape on the base tape, leading to different contact with each U-tape charging process. Overall, I believe that this experiment did a good job of showing us how objects that we don't think of as charged are part of our daily lives.